This Embryology Highlights screencast, Cardiovascular Development 4, deals with vein development. The embryonic veins that drain into the sinus venosus are the vitellin, which drains the yolk sac, the umbilical, which drains the allantois, and cardinal veins, which drain the embryo itself. The embryonic veins are bilateral. The transition from embryonic to adult veins involves a proliferation of new veins, anastomoses between veins, and selective degeneration of the embryonic segments. This image shows that embryonic vessels are bilateral. The veins are colored blue. The cranial and caudal cardinal veins drain the embryo itself. Vitellin veins drain the yolk sac, and umbilical veins drain the allantois. The cranial vena cava is derived from the right cranial cardinal vein in our domestic animals. Each embryonic cranial cardinal vein becomes an adult internal jugular vein, and external jugular veins and subclavian veins arise by budding from that cranial cardinal vein. This image shows the external jugular veins and subclavian veins bilaterally, and they have arisen as buds from the cranial cardinal vein. In our domestic mammals, an anastomotic branch develops from left to right and carries blood to the right cranial cardinal vein from the left. As a result of this shift to the right sinus venosus enlarges and becomes the right atrium. The left sinus venosus does not enlarge so much, and it becomes the coronary sinus. The cranial cardinal vein then on the right side becomes the cranial vena cava. It is fed by brachycephalic veins, each being formed by external jugular and subclavian veins. This image from a canine cadaver shows bilateral cranial vena cava. The one on the right is normal. The one on the left resulted from a persistent cranial cardinal vein on the left side. It did not degenerate. It persisted, and it drains into the coronary sinus on the left side. The presence of a double cranial vena cava is normal in rats and mice. The adult caudal vena cava and azygous vein are derived from caudal cardinal veins bilaterally. The caudal cardinal veins give rise to supracardinal and subcardinal venous plexuses, and in the adult, the caudal vena cava and azygous veins are formed by a patching together of segments of these embryonic veins. This textbook image shows 4 stages of venous development in the abdomen. Initially, we have in blue caudal cardinal veins, and they give off a plexus of subcardinal veins, here shown in green. Subsequently, they also give rise to supracardinal veins, shown in brown. And so we have this plexus of caudal cardinals, supracardinal, and subcardinal veins from which the abdominal veins are going to be patched together. Here we see later stages of development. We see an azygous vein has been formed mainly from supracardinal veins, and a caudal vena cava has been patched together from the remaining venous plexuses. This image shows what the previous image showed. We have cardinal veins in blue. They give off a plexus of subcardinal veins, shown in red, and at a later stage, supracardinal veins are given off. They're shown in this tan or brown color. Later stages of development show just how the caudal vena cava is patched together from multiple sources of abdominal veins. The azygous vein is formed mainly by supracardinal veins. The formation of veins by such complex patching together of different sources of veins lends itself to anatomical variability of veins. Next, let's consider development of the portal vein and the ductus venosus. The vitellin vein, which drains the yolk sac and the embryonic gut, gives rise to the adult portal vein, which carries blood from the digestive tract to the liver. Both the vitelline and umbilical veins contribute to liver sinusoids. The umbilical vein is the one that carries blood from the placenta to the liver. This image on the right shows vitelline veins in green and umbilical veins in blue, viewed from a ventral perspective. The portal vein, which carries blood from the digestive tract to the liver, is patched together from segments of right and left vitelline veins. Meanwhile, this right umbilical vein will atrophy, and all of the placental blood will be carried to the liver via the left umbilical vein, and it will be shunted through the liver so it bypasses liver sinusoids by a ductus venosus that forms, shown here in orange. On the left side, this image shows that liver sinusoids are formed by both vitelline and umbilical arteries. And you can see how a ductus venosus forms and how it can shunt blood, placental blood coming from the umbilical vein through the liver so it bypasses liver sinusoids and then joins the systemic circulation via hepatic veins and the caudal vena cava. The ductus venosus represents a portosystemic shunt. It conveys blood from the portal vein to the systemic circulation into the caudal vena cava. Being able to bypass liver sinusoids works in the embryo because the maternal liver is able to detoxify placental blood. Postnatally, however, a persistent portosystemic shunt that allows toxic digestive products to bypass liver sinusoids is problematic. The toxic molecules can produce neurological signs. This image on the left shows the normal adult pattern of blood flow. Notice that the portal vein is conveying blood from the digestive tract to the liver, and that blood then would pass through liver sinusoids and be detoxified before it enters the systemic circulation. This is diagrammed on the right. At the top here we see the normal pattern diagrammed. All of the portal blood coming from the digestive tract must pass through the liver before it can enter the systemic circulation. Below, we see three versions of portosystemic shunts, where blood is being shunted so it bypasses the liver. In the first instance, we have a patent ductus venosus, which is not closed. Below, we have a shunt that has developed directly between the portal vein and the caudal vena cava, bypassing liver, and another version would be a shunt that develops between the portal vein and the azygous vein, and that would allow blood to bypass the liver. You recall how these abdominal veins were patched together, and so it's not surprising that in that patch process a communication might develop between the portal vein and either the caudal vena cava or the azygous vein. Depending on the volume of blood that's being shunted, that would determine how serious the clinical signs and how clinically significant the condition would be. Pulmonary veins form as outgrowths of the left atrium. The outgrowth branches to drain each lung lobe. The lobar veins become incorporated into the wall of the left atrium as the heart grows, and so the adult left atrium has multiple venous openings in it, receiving multiple veins from lobes of the lung. This image shows early and later stages of cardiac development. On the left, we see an outgrowth of the embryonic left atrium, branching then into the lungs, and it will further branch into lobes of the lungs. On the right, we see the adult left atrium is being formed by incorporation of those pulmonary veins into the wall of the left atrium. So the left atrium has multiple pulmonary veins entering it. The embryonic atrium ends up as being the left auricle. Lymph vessels arise as outgrowths of lymph sacs. The lymph sacs develop in the neck region, in the cranial abdomen, and in the pelvic region. Lymph nodes are formed by surrounding mesoderm that invades the lymph vessel so that lymph sinusoids are formed. This concludes this embryology highlight screencast that deals with vein development.